Okay, so welcome back. Now for this example here, we've got two parts, part A and B. And so what we want to do is for each of these functions, we want to verify that the function satisfies the criteria stated in Rolle's theorem and find all values of c in the given interval where f prime of c is equal to 0. Okay, so now it's got to satisfy the criteria, which means we want to make sure that these functions are continuous over the closed interval, differentiable over the open interval. And that's obviously true for both of these because if you look at this function, they're both polynomial functions. And remember, polynomial functions are continuous everywhere. Okay? And they're also differentiable everywhere. Okay? So these satisfy the criteria for using Rolle's theorem, okay? Especially over the interval here. So over the closed interval, that's what we're looking for. So obviously, yeah, since they're continuous everywhere, polynomial functions are differentiable everywhere. There's no issues here. So now what we want to do is we want to find the second part is finding all values c, okay, in the given interval. So remember, with Rolle's theorem, let's test, forgot one more criteria. Okay, f of a must be equal to f of c, right? So let's do f of negative 2. So f of negative 2 equals what? So this is going to be 4 minus 4, which equals 0. And then f of 0 is also equal to 0. So we're good, okay? So now we want to find, so what does Rolle's theorem say? There has to be at least one c over the interval where the derivative is equal to 0. Well, how do we find that? Well, we use the derivative function, right? So now we're going to use f prime of x, which is equal to 2x plus 2. We're going to set that equal to 0. And what does that tell us? Well, that tells us that x is equal to negative 1. Okay? So that's the value. So, and obviously negative 1 is in the interval, and f prime of negative 1 is 0. So our critical value, or our c value, if you're not critical, but c value is, well, it is a critical value, is negative 1. Okay, now, let's do B. Again, we've got a polynomial, so we know it's continuous over the closed interval, and it's also differentiable over the closed interval, but we're mainly the open interval for the sake of the theorem. Okay, now we're going to also test the endpoints, right, because they have to be equal in order to use Rolle's theorem. So f of negative 2 equals what? Negative 8 minus, well, negative 8, which equals 0. F of positive 2 equals 8 minus 8, which equals 0. Now, just incidentally, both of these are 0, okay? But remember, the main thing is that the endpoints, okay, the function evaluated at the endpoints must be the same, not necessarily equal to 0. It just happens that both of these are equal to 0, but that's just incidental, okay? If these are both 2, or if they both negative 2, that would still be fine, okay? The point is that they have to be the same. So now that they're the same, now we can apply Rolle's theorem. So now we take Well, okay, so what does Rolle's theorem say? Rolle's theorem states that there must be at least one c value, at least one, could be two or more, okay, but there's at least one c value where the derivative is 0, okay? So let's find that. So f prime of x equals 3x squared minus 4, right? Okay? And so that tells us, what do we get? If we set that equal to 0, hold on. Okay, so we set this equal to 0, and so we solve for x squared, and so we get x squared is equal to 4/3. And if we take the square root of both sides, we get x is equal to plus or minus, don't forget the plus or minus, 2 over the square root of 3. Okay, and of course if we rationalize this, which we probably want to, is going to be plus or minus 2 root 3 over 3. Okay, I mean if you leave it like this, that's fine. So there's two critical values, right? So we found two critical values. So we found C1, which is equal to, I'll just leave it like this, 2 root 3. And we found C2, which is equal to negative 2 root 3, or 2 over the root 3. Okay, and that's it. That's all they wanted you to do. Okay, have a great day.